Circular motion, exercise question 30, from H.C. Verma. Look at this setup. A cabin moves in a circle of large radius r about center O with angular velocity omega. Inside the cabin, there is a smooth table. A small pulley is fastened to the table. Two masses, mass m and mass 2m, are placed on opposite sides of the pulley, connected by a string going over it. Both strings are along the outward radial direction. In the rotating frame of the cabin, each mass experiences a centrifugal force outward. On mass 2m, the centrifugal force is 2m omega squared r. On mass m, it is m omega squared r. Since 2m has the larger outward force, it will accelerate outward, pulling mass m inward toward the center. The question asks, a table with a smooth horizontal surface is placed in a cabin which moves in a circle of a large radius r. A smooth pulley of small radius is fastened to the table. Two masses, mass m and mass 2m, are placed on the table, connected through a string going over the pulley. Initially the masses are held with the strings along the outward radius, and then the system is released from rest with respect to the cabin. Find the magnitude of the initial acceleration of the masses as seen from the cabin, and the tension in the string. The key concepts. Since we are working in the rotating frame of the cabin, we must include pseudo forces. Each mass experiences a centrifugal force directed radially outward, equal to mass times omega squared times r. On mass 2m, the centrifugal force is 2m omega squared r. On mass m, the centrifugal force is m omega squared r. Now here is the crucial insight. This setup is just like an Atwood machine, but instead of gravity pulling the masses down, centrifugal force pushes both masses outward. The heavier mass 2m has a larger outward force, so it accelerates outward while mass m is pulled inward. The constraint is that both masses have the same acceleration magnitude. Let us solve this step by step. We draw the free body diagrams in the rotating frame. For mass 2m, the centrifugal force 2m omega squared r acts outward, and tension T acts inward through the string. Since 2m accelerates outward with acceleration a, we write 2m omega squared r minus T equals 2m a. For mass m, the centrifugal force m omega squared r acts outward, but the string tension T pulls it inward. Since m moves inward with acceleration a, we write T minus m omega squared r equals ma. Now we add both equations. The tension T cancels out. We get 2m omega squared r minus m omega squared r equals 3ma. That simplifies 2m omega squared r equals 3ma. Solving this, a equals omega squared r over 3. Now substituting back into the equation for mass m, T equals m times a plus omega squared r. That gives us T equals m times omega squared r over 3 plus omega squared r, which equals 4 meters omega squared r over 3. The answer, the initial acceleration of both masses as seen from the cabin, is a equals omega squared r over 3. And the tension in the string is T equals 4 meters omega squared r over 3. Exam tips. First, in any rotating reference frame problem, always include centrifugal force on every mass. It equals mass times omega squared times r, directed radially outward. Note that the Coriolis force is 0 for objects that are initially at rest in the rotating frame. Second, recognize the Atwood machine analogy. This problem is equivalent to a standard Atwood machine, where the role of gravity is played by the centrifugal acceleration omega squared r. Third, you can directly use the standard Atwood machine formulas. Acceleration A equals the difference of forces divided by total mass. Here that gives 2m minus m times omega squared r divided by m plus 2m, which is omega squared r over 3. Quick and elegant. Like and subscribe for more circular motion solutions at MAGPIEHUB.